School, when I make videos, the janitor cranks his music up, and so sometimes I have to go out and tell him to turn it off. It's like,
Like, we don't want to hear Michael Jackson right now.
no, he does heavy metal headbanging crap. It's bad. It's bad.
Like that rock.
Okay, so get a blank piece of paper. You're going to need a ruler or a straight edge of some kind, so pause this if you need to. And we're going to, this whole title, this is a heating curve. So we have a heating curve. Okay, so you're going to need an X and a Y axis. So go ahead and create that, and I'm going to shrink this down so you can see what I'm making here. So let's see. I'm going to leave some room down here so I can write on it, below it. Hang on. So my y-axis is temperature. And it's usually in Celsius, believe it or not in Kelvin. So my y-axis is temperature, and my x-axis is heat absorbed over time. So as time passes, this is how much heat is absorbed. Now, the angles, and you can have a heating curve for every single substance that's out there. Every substance has its own unique heating curve. So the length of the lines, the angle, the slope of the line, they all matter. So I'm going to draw a generic one. If that's not a particular thing, I'll probably draw out something and assume it's water because that's the easiest thing to do. But if you see the real heating curve, then the angle is important. Again, that slope of the line is important. How long the line is important and everything. So I'm not going to be too worried about getting exactly the right angles, but you can see generally what I'm talking about here. So I'm going to say 0. Let's say, I'm going to say 0 is right here. So here's my 0 line right here. So when I talk about temperature, let's put it in Celsius. And so this might be 50. Here's 100. Right? Here it'd be 150. So when I do this, if I'm talking, let's say I'm going to use this as H2O, so this will be my H2O heating curve. Then I know that below 0, I'm going to have it as a solid, right? So here's my solid. So this will be a solid right here. You guys know this. Again, anytime you get a heating curve, you look up at this stuff, think water, because you know everything there is to know about this. And right here, as it's changing from a solid to a gas, I'm sorry, from a solid to a liquid, this is the melting point. If I put MP, do you guys understand that's melting point? If you don't, if you think you're going to forget that, write down here at the bottom somewhere, MP equal melting point. That means BP equals boiling point. FP, freezing point. Okay, and you understand that when we talk about water, we know what the temperatures are. Freezing points don't have to be cold. I mean, if you think about it right now, the plastic that you're sitting at is frozen. Yes? Frozen means it's in a solid form. So freezing point, don't get so stuck in your mind with freezing point it's got to be really, really cold, because that's not the case for most things. It is the case for water. It is the case for a lot of gases that are at room temperature. It's the case for all the gases at room temperature. But for most things, I mean, look around you. Most things are solid. We don't live in a liquid world right here. So the vast majority of things that you deal with are solid. They are frozen. They are in the solid form. So you got to break some of your old habits of thinking of, oh, well, it's frozen, so it's cold, and that's not the case. So we have our melting point. Now, from that, and my angle will be different from here to the next line. The slope of the line will be slightly different. So I'm going to purposely make the slope of the line different here. The slope of the line, this is where it's a liquid, and it's going to be a liquid all the way up until the 100 degrees Celsius point. So here, I've got my liquid. And then right here at that 100 degrees Celsius point is going to be my boiling point. And again, the lengths of the lines, look at the length, compare the lengths of the lines. The lengths of the lines are really important because they tell you about how much more energy is needed. There's a lot more energy to break it from a liquid, to change from a liquid to a gas. There's more energy needed there than it is to change it from a solid to a liquid, which is interesting. So here we have 100 degrees Celsius, we have the boiling point. And then here, my last line up here, again, a different slope. This is where it's a gas. So I'm going to shrink this down so you can see all of it. So we have the solid, and you guys all know, ice or water freezes at 0 degrees Celsius. It melts at 0 degrees Celsius. So while it's at 0 degrees Celsius, it's not increasing in temperature, is it? So, okay, write that down, and then let me explain and point some things out to you guys. We talked about this in creative chemistry, so I don't know what you guys remember from that or not. But when or while a substance is changing, in the process of changing phase, the temperature stops changing, it flatlines. So when we have ice and we're getting it to melt, while it's in that melting point, the temperature is going to be, when it's slush, where it's part ice, part water, the temperature stays steady at 0 degrees Celsius. Once all the ice is gone, then the temperature starts rising again. So what happens is when it gets to that 0 degrees Celsius, that point where it changes phase, even if you crank the heat up, any excess heat you put into it goes to changing more molecules into the liquid form as opposed to increasing the whole temperature of the substance. Once it's all gone, all the ice is gone, then you have the liquid and the temperature starts going back up. When it gets to that boiling point, what's the boiling point of water? 100 degrees Celsius. When you're boiling some water on the stove and you crank the heat up, all it does is boil faster. If you had a thermometer in there, it would still read 100 degrees Celsius. So while it's boiling, it's all 100 degrees Celsius. The gas itself, it can get hotter than that. That's why you have to be careful. But while it's boiling, the temperature flatlines and it stays at that 100 degrees Celsius. Okay, stay with me just one more second. Now, our experience with this boiling is on our stove with the water, right? And as the water boils, the steam comes up, yes? And it gets farther and farther from the heat, so the steam actually cools back down and it condenses back to a liquid, right? If you have different setups, you can actually get that steam where it continues to get hotter and hotter, and you can have steam that's way over 100 degrees Celsius in temperature. So you can get huge, massive burns from steam, depending upon where you're working and things like that. Okay? Stop right there and take a break.